Okay, so last time we briefly went over something called zeta naught. Now zeta naught is defined as an infinite nesting of epsilons, and it has the fundamental sequence epsilon naught, epsilon, epsilon naught, epsilon, epsilon, epsilon naught, on and on. Now zeta naught is another fixed point, and this time it satisfies the equation epsilon sub a is equal to a, because we can imagine epsilon sub zeta naught is still just equal to zeta naught, because if we plug an infinite nesting of epsilons underneath just one more epsilon, it's still just going to be an infinite nesting. So that just equals the exact same thing. Now, before we go any further, I'll just do an example of what happens when we plug in zeta naught into the fast-growing hierarchy, just to get an idea of how to deconstruct it. So zeta naught's a limit ordinal. It has a fundamental sequence. So first thing, we're going to diagonalize and take the third element here. So we'll just plug that in. F epsilon, epsilon, epsilon naught of 3. And we remember that anything in the subscript here we can treat as any other ordinal that we've done before. So we've diagonalized epsilon naught before, and we know that it turns into omega to the omega. So this is going to turn into F sub epsilon, epsilon, omega to the omega. And I'll skip a couple steps here because we know how to deconstruct omega to the omega. It turns into F epsilon, epsilon, omega squared times 2 plus omega times 2 plus 3. So it might not be so clear how to deconstruct something like this. It seems a little messy. So let's think of a simpler example. If you remember before, epsilon 1, the way we diagonalized that is we took the third element of the fundamental sequence, which in this case is omega to the omega to the omega to the epsilon naught plus 1. Now, another way of thinking about this is we take the subscript here, minus 1, and then we add 1 to the outside to escape the fixed point trap. So this is basically the exact same format. It just has a larger subscript here. So we're going to do the same thing, take a tower of 3 omegas, and then plop this on top here. So we're going to have F sub epsilon, now omega to the omega to the omega, and then this thing with just minus 1 here from the subscript, so it's going to be epsilon sub omega squared times 2 plus omega 2 plus 2 this time, and then a plus 1 out here. So I want to make it clear that this is in brackets here. So this is the subscript, and this plus 1 is on the outside being added to this whole thing right here. And then after this, you can do some rules of exponents. So you can turn this plus 1 into a times omega on this line here. So let's turn this into F sub epsilon, omega to the omega to the omega, epsilon squared plus omega times 2 plus 2 times omega. And that omega gets diagonalized to 3. So we can put a 3 out here. And you can continue on in this fashion or whatever. This is just things that you already know how to do. I just wanted to do an example to see how you get past the zeta naught here. Because after this, it really is just part of the epsilons, which is what we did in the last video. Now, to get beyond zeta naught, because we run into the same problem of having to escape the fixed point trap, we basically do the exact same thing. We just add 1. Because no matter how big an ordinal is, you can always add 1 to it and get past. Because you can imagine plugging this into the fast-growing hierarchy. It's not equal to, I don't know, I keep on doing that. Let's say we have F zeta naught plus 1 of 3. This breaks apart into 3 copies of the zeta naught function. So F zeta naught, F zeta naught, F zeta naught. Now F zeta naught of 3 is a very, very large number, as we know. And what would happen is the output of this gets put into here, diagonalized, and this turns into a nesting of epsilons that's this many deep. So clearly we have a bigger ordinal. So this adding 1 always works with ordinals, you'll find. Now the next thing we want to do is to create zeta 1. We want to create a fundamental sequence that has the properties of escaping the fixed point trap as well as satisfying the equation epsilon a is equal to a. So how we do that is we take epsilon sub zeta naught plus 1, and we create the next element, which is going to be epsilon sub zeta naught plus 1. And this goes on to an infinite nesting of epsilons with sub zeta naught plus 1 at the bottom, whatever. So that's the second time we reach the fixed point, because clearly epsilon sub zeta 1 is also just going to be zeta 1. Now, to give you an idea of how this breaks apart in the fast growing hierarchy, we'll just do another example. I'll do one more element here. Of 3. So this is a limit ordinal. It has this fundamental sequence. So again, we take the third element, which is this here, and this turns into f sub epsilon 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 sub zeta naught plus 1. Now this right here, we're going to do that thing where we take the tower of omegas and plop this on top here. So this turns into f epsilon epsilon, then omega to the omega to the omega to this minus 1, which is going to be epsilon sub zeta naught, and then plus 1 right here. So now something happens, because this is all by itself. This is going to collapse to just zeta naught. So we can rewrite that. F epsilon epsilon omega to the omega to the omega and zeta naught. Oh, I skipped a step too. So basically, I was implying basically that this... oh, no, we're good. Sorry, yeah, I'm getting confused here. Okay, so yeah, so this collapses to zeta naught plus 1. Now the next step, which is what I was thinking of, is we take this plus 1 and use rules of exponents to turn this into a times omega. So we'll do that. F epsilon epsilon omega to the omega to the omega zeta naught times omega. Now another thing happens here. This collapses to zeta naught as well, because if you remember, any ordinal that's bigger than epsilon naught is going to get collapsed with an omega. So actually, zeta naught satisfies two equations. It satisfies this one here, and also this one here. So as we get further and further into the ordinals, they start satisfying new equations, but they also satisfy all the previous ones as well. So you have to know when to collapse certain ordinals. So we can do this step here, and we can diagonalize the 3, so we end up getting something like epsilon epsilon omega to the omega to the zeta naught times 3. And it just keeps going from here or whatever. You can do the deconstruction on your own if you wish. I'm not going to go until we reach a successor, because clearly it's going to take a very, very long time. It's going to take pages and pages of math. And from here, it's already things you know how to do, basically. So we can imagine creating new fundamental sequences for each of the zetas. So we can create zeta 2 by taking the fundamental sequence epsilon sub zeta 1 plus 1, epsilon epsilon sub zeta 1 plus 1, and so forth. And the same way we can create zeta 3, zeta 4. We can have the infinite ordinal omega in the subscript, which would have a fundamental sequence zeta 1, zeta 2, zeta 3, and so on. We can have zeta sub epsilon naught. We can even have zeta sub zeta naught. And then as before with the epsilons, we can have an arbitrary number of nested zetas. And an infinite number is something called eta naught, which has the fundamental sequence zeta naught, zeta, zeta naught, zeta, zeta, zeta naught, and so forth. So now we kind of run into a problem, because this exercise becomes kind of arbitrary. Because you can imagine doing the exact same thing with the etas now, coming up with new fundamental sequences, and eventually getting to a point where you have eta, sub eta, sub eta, sub eta. And then you have to come up with a new Greek letter to enumerate that, and so on and so forth. Now, there isn't an infinite number of Greek letters in the alphabet, so clearly we need a stronger concept to deal with all these. And that'll be in the next video.